Air traffic control communication is one of the most fundamental systems in IFR flight operations. It's the invisible coordination layer that keeps aircraft separated, sequenced, and safely routed through complex airspace structures. But just like any system in aviation, it's not immune to failure. Radios fail, headsets die, avionics glitch. And sometimes, pilots find themselves in the worst-case scenario: lost communications in IMC, mid-operation, with no immediate way to talk to ATC. So, what actually happens when communication goes dead in the middle of an IFR flight? And more importantly, how does the system expect you to behave when everything goes silent? To understand that, imagine a typical IFR flight plan. You're departing Morgantown, West Virginia, heading toward Hagerstown, Maryland. Your route is already structured. Departure from Morgantown. Proceed to the first fix, O-Town, then direct to the Indian Head VOR, joining Victor, 268, and finally tracking toward Hagerstown VOR and your destination airport. It looks clean on paper, almost predictable. That predictability is the entire backbone of IFR flight planning. When you receive your IFR clearance, you're not just getting a route, you're getting a set of expectations that define what you do even if everything breaks later. You're cleared via O-Town, Indian Head VOR, Victor, 268, Hagerstown. Maintain 5,000 feet initially. Expect 7,000 feet 10 minutes after departure. Departure frequency 121.15 and squawk code assigned by ATC. At first glance, that looks like routine flight data. But hidden inside that clearance is the survival logic for lost communications. Now, imagine you take off. Everything is normal. You're climbing through controlled airspace, engaging autopilot, switching from tower to departure frequency, and tracking your route toward the first fix. But then, it happens. Your communication system fails. Maybe COM1 goes silent. Maybe both radios drop. No response from ATC. No readback. No confirmation. You're now flying IFR in IMC with lost communications. This is where most pilots make a dangerous mistake. Mentally, they start thinking the priority is fixing the radio. But IFR lost comms procedure is very clear on one thing: fly the airplane first. Before troubleshooting anything, before switching headsets, before panic sets in, the aircraft must remain stable. Heading, altitude, and navigation are priority one. Automation, if available, becomes your stabilizing layer. In our example, the autopilot is already tracking toward O-Town and climbing to 5,000 feet, which was the assigned altitude in the IFR clearance. Once the aircraft is stable, the next step in the lost communications protocol kicks in. Communication failure must be signaled to ATC. Even if they can't hear you, they might still see you. That's where the transponder becomes critical. You set squawk code 7600. That single code is a universal signal in IFR flight operations that tells ATC, lost communications. Follow contingency procedures. It doesn't fix the problem, but it activates a predictable response chain in the air traffic system. Controllers immediately know how to treat your aircraft, what separation standards to apply, and what assumptions to make about your behavior. Now the system is operating in partial blindness but still structured blindness. Here's where IFR regulations, specifically FAR 91.185, take over. This is the legal backbone of lost communications procedures, and it's built entirely around one concept: predictability. ATC doesn't need to talk to you if they can predict exactly what you will do. That prediction is based on your clearance, and it follows a strict hierarchy: assigned route, then expected route, then filed route. Assigned altitude, expected altitude, and minimum safe altitude all become part of the decision chain. In our flight, you were assigned 5,000 feet. You were also told to expect 7,000 feet 10 minutes after departure. That expect instruction is not casual, it's a contingency instruction. If communications fail, that expected altitude becomes your next action point. So after departure, you remain at 5,000 feet initially. Then, 10 minutes after your departure timestamp, let's say 26 minutes past the hour, you climb to 7,000 feet. This is not optional. This is procedural predictability under IFR Lost Comms rules. Meanwhile, navigation continues along the filed route. O-Town, Indian Head VOR, Victor 268, and onward. If radar vectors had been assigned prior to failure, you would continue those vectors until established on a published route or fix, then resume the cleared routing. Everything is structured. Nothing is random. Now, we move into the navigation and altitude conflict layer, the part that makes IFR Lost Comms logic more complex than it looks. You may encounter multiple altitude constraints: MEA, assigned altitude, expected altitude, and minimum safe altitude. The rule is simple but critical. Always fly the highest applicable altitude that satisfies terrain and procedural requirements. If the airway's MEA is higher than your expected altitude, you climb to the MEA. If minimum safe altitude near terrain is higher, you respect that instead. In Lost Comms scenarios, safety and obstacle clearance override convenience every time. As you approach the Indian Head VOR and transition onto Victor 268, you're now deep into en route structure. This is where IFR airway design becomes your fallback navigation system. Even without ATC input, the airway structure is predictable, charted, and safe. But the real turning point comes next: the clearance limit. In most IFR clearances, the clearance limit is your destination airport, in this case, Hagerstown. Under FAR 91.185, if communications are lost, you proceed to your clearance limit and then begin an approach from a fix that allows you to initiate an instrument approach procedure. That means you don't just arrive and descend randomly, you transition into a structured approach environment. So you plan the ILS Runway 9 approach. You identify the initial approach fix, such as COVIC. You prepare for localizer capture, glide path intercept, and final approach segment execution. But you also respect altitude constraints until established on the approach, never descending below minimum safe altitude prematurely. Even without ATC clearance, the approach itself is still standardized. The system assumes you will fly the published procedure exactly as charted. Now add timing logic into the equation. IFR Lost Comms procedures rely heavily on time-based expectations. You may be instructed to expect further clearance at a specific time EFC timing. If that time arrives and no communication is restored, that becomes your trigger point for the next procedural step, such as holding or beginning an approach. It's not guesswork, it's synchronized timing logic between pilot and ATC. In some scenarios, you might regain communication before reaching the destination. ATC might clear you for an approach, assign a fix like COVIC, and issue holding instructions with an expected further clearance time. If communications fail again at that stage, the EFC time becomes your anchor. You remain in the hold until that time, then proceed as planned. Everything is designed so the aircraft never becomes unpredictable. But there's another layer here: pilot decision-making under uncertainty. Because while regulations provide structure, the pilot in command still carries emergency authority. If conditions deteriorate or timing conflicts create risk, the pilot can prioritize safety over procedural strictness. That might include diverting to an alternate airport, selecting nearest VFR conditions if available, or declaring an emergency by switching to Squawk 7700. That code changes everything. It escalates the situation from procedural lost comms to full emergency priority handling. Ultimately, IFR lost communications procedures are not about perfection. They're about predictability under failure. The system is designed so that even when radios go silent, aircraft still behave in ways ATC can anticipate and safely manage. Because in IFR flight operations, silence doesn't mean chaos. It means procedure takes over. And that's the core idea behind IFR lost communications procedures. When everything goes silent, the system doesn't fall apart. It shifts into a predefined logic where routing, altitude, timing, and approach sequencing all work together to keep the aircraft predictable and safe, even without a single word from ATC. Because in IFR operations, communication is important, but predictability is what actually keeps the sky organized when communication fails. So, whether it's climbing to your assigned altitude, transitioning to your expected altitude after 10 minutes, following Victor Airways like V268, or executing a full ILS approach into your clearance limit airport like Hagerstown, every step is already designed to function even in complete radio silence. And that's what makes IFR structure so powerful. It doesn't rely on perfect conditions. It relies on procedures that still work when conditions are far from perfect. If you like this kind of deep dive into aviation logic and real-world IFR scenarios, do us a favor, like the video, subscribe, and turn on notifications. It really helps the channel grow and lets you stay updated with more breakdowns like this.